Welcome everyone. This is going to be the last one in this, in this course from me. This lecture on ML. There are two topics which I want to bring it up to you. One is image recognition. Did I speak with you or not on that image recognition?
Image iteration?
Okay, so we are going to go over image recognition, and the second part is reinforcement learning. Okay, third one is also there, RNN, which is recurrent neural network. I don't think we will have enough time, so maybe I'll record it and post it for you in the future within a week. My notes are somewhat lost actually in the process of yesterday. I was talking to you, right? Supriya. I'm still having some difficulty to look at some of the partial notes that are required. I don't know what happened, but anyway, coupled with what happened yesterday, the program, I have those difficulties. The program and the presentation deck is missing for recurrent neural. So I will record that and send it to you. As usual, you should know that you are always welcome to come and attend a class in the future also. Okay, that's another thing. Sometimes we change topics, to catch up with the latest topics people need. Okay. So the two needs, very important needs in data science, will be very different from statistical learning. Okay, is the what is called the big data analysis, which involves unstructured data, which is talk, text, images, videos, all those things. Okay, and voice. That's what talks I meant. All those things. So we are going to address one of them, that is image recognition. Okay, but the deep neural networks, which is the foundation for all these things, you can, once you learn the neural network, and one example of that, because of the time requirements, one big data analytics, which is image analysis, you should be able to pick it up. If not, come back to just join in future, or especially I'm going to record a RNN and post it for you. Okay, how does that sound? Those are the two things. And then I said reinforcement learning, which is a big deal. But that big deal also has its own limitations. See, that's the beauty of humans, right? All said and done, forget about AI beating us. I don't believe that. Okay, and reinforcement learning, which is a phenomenal development, because through the reinforcement learning, we were able to develop a computer AI which bet the world champion. It bet the world champion absolutely. So you might be wondering, so why am I saying that no, it will never, humans will always have an edge with the AI? That's a very general, very one-sided, biased type statement, but I do mean there is a reason for that. I'll tell you why. Okay, I said reinforcement learning bet the world champion in Go game. Okay, Go game. It's a Chinese game. There are so many variations in Go game, and it bet the current world champion. The thing is, reinforcement learnings are always within a box solution. In other words, a box is there. Within the box, how the rules are given, how to move around, how to play the game. Right? A game is always a structured one, right? It doesn't have. It's not outside the box situation. Within the box situation. Do you understand what I'm saying? In other words, a game is, a game has certain rules to follow. That's it. And that rules leads you to whether somebody will win or not. Very simple, right? It is not outside that rule. That's what I'm saying. Because the set of rules are very well clearly identified, and you give a right reward system, right way of making a decision. You go over a sequence of steps, and then that reward gives you that sequence of steps gives you a reward, and then you make the next decision. If the sequence is rewards is going down, then you don't make that direction at all. Am I making sense? That's how the reinforcement learnings are built, and it is still not possible to use that in the real world. Am I making sense? There is a real world there. That is, a champion beating a champion, human champion is a real world problem. But yet it is not a very general AI problem solution. Am I getting along? Okay, so we are going to find that it's a beautiful, beautiful, amazing solution that is useful for games, and that so happens reinforcement learning is very popular in games. Okay, because of that. Why? Because the rules have to be, final set of rules have to be known. See, with humans, they will come all the way, and then suddenly they will change the rule of the game. They will bring in something else which AI may not know. You know what I'm saying? But humans know it. Am I making sense? Right? Because of that, reinforcement is a phenomenal development. It's great for within the box solutions, mostly for games. But if you go outside of games in practical life, reinforcement learning is yet to find out its important applications. Are you with me, everybody? So let's talk about the two great developments. One is, I talked about image recognition. Let's just do that first. Here it is. One moment, please. All right. So so let's go over. Are you able to see my screen? Let's go over image recognition. And very interestingly, there are many variations of image recognition. So you will see two of them. One, I will teach what is called the CNN, which is convolutional neural network, and then you will see something called pixelized total neural network. Okay, are you able to hear me?
Yes, sir.
Okay, all right. So you all know that the neural network is a representation of our brain, and the fundamental concept to that is what is called a perceptron, which is a simplified model of a biological neuron. Okay, so a perceptron is each one of these, okay, is a perceptron. Okay. So, for example, this is a neural network. It starts with one input here, and it goes through this network. This hidden layer. I'm sorry. You're talking about the input is at the bottom. Not usually it's left, right? But here this input is bottom. These three inputs are feeding to the first hidden layer, and which is creating a two output layer neurons. Okay. So this is how many neurons are here? 3 + 4, 7, 9 neurons are there. 9 perceptrons. Okay. Basically, neurons. The mathematical representation of that is what is called the neuron is a biological representation. Perceptron is its equal and mathematical representation. Okay, and this is a multi-layer perceptron, and here we have, as I said, 3-layer network. Here, input layer, hidden layer, and output layer. Are you able to see what the screen pictures? Input layer, hidden layer, output layer. Okay. Now, we all know that the fundamental way, the way it is operating, the neural networks are operating is as follows. What is it? You take the input at every stage. This is at it could be part of a hidden layer neuron, or it is the output layer neuron. Okay, so at any neuron level, you are taking input from previous set of neurons that are connected to it. Previous set of neuron. Here there are n neurons, or it's really the circles here, but just as input we are saying, and all these inputs are going into this neuron, and then the way it is going is always what is called the product sum. Do you recall that one? Okay, some product is Excel function, right? You understand what is some product, Excel function, right? So you have the input and then the weights. Product sum, right, or some product is what is A is as the input first. and then you do a transformation, what is called the activation function. Everybody is good? You apply an activation function on that. So that activation function is usually a sigmoid function, okay, which is a logistic function. It can be something else also, but sigmoid we have. We also talk about tan H function. We also talk about actually what is called the radial basis function, okay. But we'll come to that as an example discussion about how to use radial basis function later on. Okay, some other time, some other lecture, not here today. So you can see that this is the output out, coming out of the, coming out as the value inside this neuron. It's the output taking care of the weights as well as the inputs and applying a activation function. Everybody is good? There are many other activation functions. There is also what is called ReLU. We'll use actually ReLU, okay? ReLU function. That is rectified linear units, okay. It's a linear function, but then we rectify it up to certain range, rectify it with a different value. So that is how it happens. So there is an attachment here, I think this is what, let me see whether it is the same as what I have shared with you earlier. Yeah, it is the same as I shared with you earlier. Okay. So that is the, what happens, so you apply this for every neuron, right? In this case, we are talking about here all, the inputs are, 3 inputs are feeding it here, and then the, activation applied, product, some product, right? Some product here, 3 inputs and 3 weights. And some product here, 3 inputs and 3 weights. Some product here, 3 inputs and 3 weights. And some product here, 3 inputs and 3 weights. There are so many different weights, so there are actually, 12 weights are there, right? You have, everybody agrees here? 12 weights are there, but the weights coming here, coming into this is not W1. Let's say coming from this W11, W12, W13. 1 refers to this. So W1 times this input plus W1 times this input plus W12 plus times this input plus W13 times this input is going into this, and then you apply an activation function. There is a value there that becomes input to this one. In the same way like this, W21 times the input value here, W22 times the input value here, W23 times the input value here. So that's a sum product or product sum. I think sum product in Excel it's called sum product. Okay, sum product, and then apply the activation function. That becomes the input to this this cell. Okay, like that. You calculate every one of them. It's just a sum product, activation function, and then go to the next layer and so on. Everybody is good? That's how the neural network happens. Very, very simple. Even though we say brain this and that, it's mathematically it's a very simple architecture. Everybody is good? Yes, I'm just repeating. Okay. Now, but what happens after you go there? What do? You compare it with the expected output. So remember, it's all for supervised algorithm, which means you know the outcome there, right? And that is what we are supposed to have. You compare it with that, then the difference becomes the error. You back propagate the errors so that the weights are recalibrated with the errors. Everybody's good. Recalibrated and then recalculated. All these weights are recalculated now. Now we start back and once again the next epoch. It's called next it's called next iteration, not next epoch, next iteration. Okay, so that we keep on doing this until the errors are the error difference with the outcome from the network is reduced below a certain level. Everybody's good? That is our approach. We keep doing this again and again and again, and then we will get a converged set of weights for every one of the arrows. Every one of the arrows talks about a weight attached to the input. That's it. That's a problem. How we solve it? Now, the back propagation is uses this derivative because you want to know how the weights needs to be changed. That means how the weights needs to be changed is given by the gradient or the change in the gradient values of the activation function. You see what this is the activation function, right? So which is a logistic function in this case. and the gradient is this one, which turns out to be, interestingly, look at this one. I'm sorry. It turns out to be the gradient times 1 minus gradient. Okay. In fact, this is also the variance in the p probabilities in terms of the p's. See, if you have a Bernoulli, which is a yes or no type answer, which is what the classification is all about, right? Listen, look at me and listen very carefully. The Bernoulli is yes or no variable, right? Bernoulli is yes or no variable, random variable. Everybody knows that. Bernoulli leads to binomial, right? Sum of n Bernoulli leads to binomial distribution. Number of counts of successes, right? Number of successes. So Bernoulli is basically the classification, yes or no, this class or that class. And Bernoulli variance is, if you recall, it is PQ. Bernoulli variance is PQ, and that is exactly this. The P is represented, the probability is represented as a logistic function. Okay, but you can see P times 1 minus P, which is Q. So very interesting, and you can keep that in your memory, because what you are saying is your back propagation. Think very carefully. In the back propagation, you are basically adjusting for the spread in the estimate. Okay, spread in the estimate, and that is what is helping you to modify your weights. Okay, all right. Anyway, so what happens then? You give enough input. You recalibrate the weights and so on. And eventually you build the network. You got the network, and now you can apply it. That's what happens. And how do you build the network? Again, you keep taking some samples, random samples. Okay, remember very carefully this step. Some random sample, a batch of random sample, and run through that batch of random sample, one full iteration to find out the weights. That is one epoch. Note down this. An epoch is taken a random sample, collection of samples from the training set, and run it through the full network to determine the right answer. Right answer for the weights. Okay, that is one epoch. And we will run many epochs, and so we need to define how many epochs to run, because the more the number of epochs you take, you get a better average result. Everybody understands that, right? Average is always a better result than one sample, right? Okay. All right. Now you got an epoch, you got a sample, you got weights. You have to know all these things, right? You got weights, and then you have errors for convergence, error differences for convergence, and then finally the performance of the model. All these things we are going to call in to get our answers. Okay. So let's, this is the foundations. Now, where does the image recognition comes in? Take a look at this one. So this is a common picture that you have been working. Actually, you work many times, you work on this. This is there are 3 types of flowers, right? Iris flowers, there are 3 types. This is one type of flower. And what are those 3 types of flowers? I'm just going to use this as an example to talk about how do we make it into a data point in the case of images. That's the only purpose why I'm using this one. But in the with actual example, we are going to look at 10 different images and let the computer decide. Given a new data, new image, it should say, oh, this is a pullover, t-shirt, or this is a shoe, this is a boots versus beach sandals. This is the pants, this is the shirts, things like it's going to decide. Now, an image has basically, an image is a combination of RGB. You all know that, I suppose, right? RGB, that is red, this combination of red, blue, green color. Okay, and those the intensity of different combination gives you millions and millions and millions of colors. Okay, and how many different variations, you can very easily find that out, because R has values between 0 and 255. Everybody knows that. That is so many variations of R between 0 and 255. In numerical form, you can say that. And then likewise, green is 0 to 255 and blue is 0 to 255. So the number of colors is, total number of colors is 256 times 256 times 256. which is 256 is what? 2 power 8, 2 power 8, right? 2 power 8 times 2 power 8 times 2 power 8 times, so 2 power 24 is a huge number of colors. I mean, we human cannot comprehend the differences, but machines can find out because they are numerized. Understand what I'm saying? They are numerized, machines can understand only because of numerical value. Isn't it interesting that the whole idea of image is just a number? That's what I want to impress on you. Okay. For practical purposes, for example, the violet color is basically the human commonly known what is meant by violet is a combination of these 3 different numbers. So I have numerized the color with these 3 layers of numbers, 3 layers of numbers. Okay. Magenta is these 3 layers of numbers. Orchid color is these 3 layers of numbers. There is a question? Okay. Now, what I'm going to do is I'm going to take, for illustration purposes, because for image recognition, you don't need a color. You just need the shapes, right? The edges. That's what, the computer has to know. Okay, even human eye, that's what we want to know. Sometimes we use colors differently. Yes, I agree. But for practical purposes, in this class, I'm going to use only gray color. So we are going to take only black and white. Only one layer. That's my point. Only one layer of the image, which is black and gray color. Everybody's good? I'm not going to use colors. Now, what is meant by understanding an image? Think about it. Forget about all these 0, 1s and all those rectangles and sizes. Is that correct that wherever the intensity is in the picture, that is what is getting your attention? Yes? Intensity. Yes. Okay. So intensity of black and white, that's all it is. How black it is, how white it is. That differentiation is what matters for identifying the shape of an image. Now, what it also means is that I introduce the word shape. So it is the intensity and the edge, how the edges are. Everybody's good on that one, right? So intensity and edges is what determines a shape. That's an important conclusion. So how do we get that information into the computer? Right? We understood that the intensity is understood by just purely the numerical representation of the intensity of black and white. Okay, the continuity of such numbers determines the outline or the edge. Certain continuity and of this intensity of black and white, intensity of gray determines the shape of an image. Okay. Now, how do we get that for the machine? So machine doesn't know the outlines. Machine doesn't know the edges. So what we can do is because we give thousands of samples to the machine. That is one advantage the machine has. Okay, even children need to learn only that way. Maybe they don't need thousands, but they realize with 10 pictures they will realize that, or 20 pictures they will realize. The kids learn, that's all. We all learn. Okay, how do you teach a kid? Oh, this is cat, this is cat, this is dog. You keep telling that 10 times, to 15 times, then the kid knows it, right? The same way, but what is the idea of telling the machine that this is cat versus this is dog? That is the issue here. So what we want to do is, we take each of the pictures and then we take small regions from the pictures. Okay, small regions, and then we scan that region, scan the picture with that region. Small region we take, and then small region is something that we took out from the pictures. It's possible. We can do that way actually. We can do it any other way, but that's one way. Okay, you take a small region and scan it across 10,000 pictures. Cats will always have something of a different type near the ears, different from dogs. Agreed? Yes. But it is coming near the face. It's coming near, in a certain part of the body. So the edges are connected to the small regions that we select as features. They are called features. Everybody's good so far? So you take millions of small regions from the given pictures, scan the same region, you scan it on 10,000 times if you have 10,000 pictures. And it's simply going to tell you, yes, this region is available, this matches well with the pictures in a certain part of the region. Everybody's good so far? Of the original picture and the new picture, picture 1, picture 2, picture 3, it's going to say that. What is the intensity level and which part it is happening? Which part and what is the intensity level? Everybody is good so far? These are two important things. And we can get that information by what is called the convolution operation of the image data with the small features that we pulled out from all the pictures. Are you with me, guys?
Yes.
Excellent. So here is an example of simple numerical calculation. So let's say this is the feature type. Okay, the feature type is this. You pass it through the image. And then what is meant by passing it through? You take product sum. The product sum seems to be all over. Okay, product sum. So if I take this is the green one is let's say the picture. We are scanning using scanning the picture using this feature. Feature comes from basically comes from our images, right? Feature, and when you scan it, you want to know whether it has how much intensities are there, how much intensity. So you basically you scan this, take a product sum and put it here. So this picture size is 5 by 5, right? Just for illustration, we'll come to the real one. 5 by 5, and our feature size is 3 by 3. So when you run this one, you get the output maximum 3 by 3. Do you agree with me? You need to do some padding and so on. Don't worry about those right now. But if you run it through this one, there are only 4. There are some here also you can get, but those are all reduced. Your features don't get full attention because you're not. If you get some number here, that means you are going to get effect only from the 2 columns, right? So let's not worry about that right now. There is a padding issues. All those things will come. But the point is, here there are more ones here. There are 4 ones are here. That's what it means in relation to this feature. In relation to it's relative to the feature only. Okay, I got 4, and then you run it here. I can move this here next level. How much I will get? I will get 1 here, 0, 1 here, 1 here. So I get 3 here. Do you agree with me, everybody?
Yes.
Okay. Like that, I can fill up this one. But it tells me I have reduced this image 5 by 5 image to a smaller size to tell me which part has the maximum intensity. Is that do you agree with me? Which part of 5 by 5 has maximum intensity? I can figure that out based on this one. Everybody is good. So cats will have only a certain parts of that will be having intensity, high intensity compared to dogs. And you combine that with thousands and thousands of pictures, and then use that into a final what is called a fully connected network. Fully connected network means because we are going to have this one. This is going to create this this feature is going to, and there are going to be thousands of features. It's possible, right? There are a lot of features I can use. So I will create lots of different 3 by 3 matrices, and then I will further continue to subsample this, reduce this again and again and again. Eventually, whether this particular feature exists or not. Everybody understand? And then I'm going to create thousands of features I can if I want to, right? But those thousands of features are basically determined by the size of the picture, right? How many thousands of features are going to come out is determined by the size of the picture. Everybody agrees? Is that making sense? Gauri Shankar sir. Okay. So these are the important concepts. Features, which are okay. You can say like this also. And that means because otherwise sometimes the words may get mixed up between me and the listener student. So features are part of this process. Scanning, or what is called the product sum operation, that is convolution, is important. And then what is the size of the picture is important. Because if I have a huge picture, I'm going to have huge number of, this is going to become huge. I still don't know whether this is enough for me to stop saying that, no, this place, if I have it, it refers to, it refers to cat or it refers to dog. So we will keep on reducing the size until it becomes small enough. Then I can say, okay, that network is architecture is good. I can do the final fully connected neural network, which you have done. Fully connected neural network is basically all inputs going into some output. Okay, all inputs going into some output. So we will convert this into a regular neural network like this. That is the point I'm saying, right? We will convert this into a regular neural network like this, and then I apply this kind of algorithms, back propagation, and then I get the answer. Everybody understands the strategy here?
Yes.
Very good. Very good. All right. So that is what we are going to do. So here is an example with, actually, some kind of rat here, right? Mouse maybe, right? So this particular feature is coming from this one. See this one, what I'm saying, or maybe this one, it could be this, not this one, this, because the shape, is more aligned with this, right? So we have this, we have this mouse should be actually the fully, it should be pixel representation of filter. This is the filter, okay? This is the filter, it refers to this one. But the mouse picture will have this all over, wherever it's dark, black, you will have very close to 255. Remember that, what I'm talking, okay? So when you scan this on the picture, it captures here high intensity. Here it will not be high intensity. Nowhere else will be high intensity as much as it is here. Everybody good? Right? And that is what in fact happens. I scan that one. If I scan this is remember, this is the scanner, right? This is a huge picture is there. My scanner is this size, 3, 6, 7. 7 by 7 is my scanner. And this is probably, if this is 7 by 7, we are talking about, probably 10 times, 7 times this one. Okay, so it's probably, we are talking about 49 by 49. Right? Something like that, or maybe 70 by 70. Okay. So when you scan, when you interact that scanner, then if this is the part of the mouse, then the product sum, right? Product sum is going to have the same structure here. Rest of them are going to be 0. That's what it is. So this product sum is going to be this one, multiplication and summation, right? A large number, 66600. Somewhere in the 70 by 70, you are going to get this number 6600. Everybody's good? That's what you're saying. And that will happen only for mouse. If it is a dog, it won't happen. Okay? So we use this kind of simplified, reduced form information to figure that out, whether it's a cat or not. That's as simple as that. So image recognition turned out to be a numerized problem. Intensity and placement of the values is what matters in differentiating the images. Intensity and placement of the full picture. That's what gives us the image analysis. So and remember, every time, as usual, there is a part here, there is a data reduction part, and then fully connected neural network part. You reduce the data in many layers. So how many layers? It could be many layers. I know here's an example. So after you do the first scanning, first convolution, you get this one. And then I sample. I again do a 2 by 2 sample. This time, the filter is I maximize where is the, I take, this is the, remember, this is the output from the first scan. Please listen very carefully. We did the scanning, you got this output. This is the second step. What am I going to do? I still want to find out where the maximum signal is. So the maximum signal, so basically reduce the size of the matrix of numbers. So here it is 4 by 4. I'm further reducing it into 2 by 2. Do you see what I'm saying? How will I do it? I take a 2 by 2 filter, and then I say, what is the maximum here? 6. And then I go to the next 2 by 2. It is 8 here. Next 3 here, and then 4 here. Still, the maximum is happening in this place. Do you agree what I'm saying? So I keep doing this repetitively. Scan, pool, max, find out the max pool, scan, pool, and then finally reduce this again further into a fully connected network. Is that clear, everybody? Fully connected neural network. And then I solve the problem using neural network. So there is a data reduction step in the convolutional neural network, and then the predictive step with using the neural network. So neural network doesn't start immediately. The first, we go through a data reduction step, which it talks about intensity of the images, where and how much intensity. That is what we are capturing to find out the image prediction. So let's take this one as a ship, kind of ship, right? Looks like ship, yeah. Input layer. So yeah. Okay. So again, in this case, convolution layer is you numerize it and then scan it. That's what the convolution layer is. And then subsampling layer is reduce the, you take, subsamples above after the numerized values, product sum values, right? Remember that. Scan the images with the features. And then, and I have here four layers here because I have 4 features. If I have 10,000 features, then I will have 10,000 of them. Everybody's good? And then I reduce the size of this, because I want to find out whether it is, left corner, right corner, left corner, left top corner, right top corner, left lower corner, right lower corner. I want to, come up to that level, right? So what happens here? I reduce that, and then I keep reducing it, subsampling. Again, I can do a convolution. Okay, convolution. Okay, and then subsampling. I can do many times like this. Eventually, I come up with, in this case, it so happens that 6 feature maps, 4 feature maps initially, another subsampling, another 6 feature maps on this one. On the subsample values, I do again a feature mapping. So I have 6 feature maps, and then I create a fully connected multi-layer perceptron, and then do the neural networks. Is the strategy clear to everybody? Is there anything that I can explain further? This is it. Very simple. Okay. This is one way. So here is the image, handwritten images, but I'm going to do actually handwritten image. I will give it to you as a lab work. I'm going to talk to you about some retail images, okay? But I will explain here nonetheless. So there are so many of these examples are there, and a single sample this is the 4, right? The 4, but 4 is written in so many different ways. We see this one, but they all have certain patterns. That's how our brain connected it to an image. And so we can follow these ideas to get our answers. Now let me go to TensorFlow. So in this one, I'm going to use Python. Okay, we can use R also. I kind of trying to look at this R files versus Python files. Python is very good. R is there's, I would say, a small unless you want to follow R, that's okay, but otherwise I would say there is an advantage in Python because there are a lot of developers. There's a lot more developers in Python. All computer scientists use Python. They don't touch R in general, as was said. Okay, so you get a lot of support in Python. So there is a TensorFlow you can install. You all know how to use IPython notebook, right?
Yeah.
Right? Okay. And you all know how to install, uninstall packages, for IPython. You basically have to do Anaconda installation, and Anaconda has a navigator, it gives you so many other things, Jupyter Lab, Jupyter Notebook, including VS Code. Okay, you can create VS Code and work within the Anaconda. So I use 3.6 version of Python, and then Jupyter Jupyter Notebook I use. That's what this one is. So I have installed TensorFlow. TensorFlow is created by Google. They are creating their own operating system. They are creating their own AI platform, and AI platform uses TensorFlow. Okay, and they also have tensor processing unit. There is a chip they created also, like CPU, GPU. There is a new chip called a TPU, tensor processing unit, and that is invented, created, marketed by Google. Okay, so because they are trying to build the future of computing platform, for AI. Okay, and TensorFlow is part of it, Python is part of it, Python notebook is part of it, and TPU is part of it. And TPU is very, you can stack the TPUs, so many of them, very easily. That's the beauty of, you can create a parallel computer very quickly with TPUs. Of course, you and I cannot buy TPUs very easily, okay? Unless you are a research organization, you kind of go and bring a look, hey, we are doing research in, TensorFlow, AI, we are a research institute, can you give us some chips? Then they will, you can buy them. I don't think you can easily buy, an individual cannot buy it, okay? But you can as well buy the cloud GPU. Do you understand what I'm saying? Cloud, no, not GPU, cloud GCP, cloud GCP. Do you agree? Do you understand what I'm saying? Google Cloud Platform. There they are using GPUs, so you don't have to go and buy the hardware, build yourself supercomputers. In my opinion, it's a waste of time. Unless you are just a fundamental foundation researcher. Are you with me so far? So you just get your time with the GCP, Google Cloud Platform. So we can run this in Google Cloud Platform, but this is basically the codes mostly taken from Google. Okay, this from the Google Colab. Okay, everybody's good. Did you hear my words? Colab. Okay, Google gives you Colab free for you to try. So okay, so I imported TensorFlow. So they also made available this software TensorFlow for public to use it. Okay, so and TensorFlow uses what is called Keras. Keras is a deep learning package. Okay, developed both for Python and R. So we are going to use TensorFlow, and then from TensorFlow we import Keras, and then from NumPy we import NumPy. We also import Matplotlib because we want to see the images. Everything is good so far, and I just wanted to download, install, and find out what the version I have. So it is just checking out right now, and initially it has to connect to the various stuff in the background. So it turns out that TensorFlow version is 1.15. Okay, there is also TensorFlow 2, but I don't want to use that term. And Keras has some data sets, and the fashion images is one of the data sets. Okay, so we have something called Keras.datasets. So now datasets is an object within Keras, and then within the datasets we have what is called the fashion MNIST. Okay, so that's what we are going to download and store it under fashion.mnist. And this fashion.mnist has both train images and train labels, as well as test images and test labels. And this is what is called, this method in Python is what is called, you can basically split the right hand side. If you put the left hand side the names, and the right hand side the object name, it splits it accordingly. It's a very interesting way of pulling out members of the object. So far so good, everybody. I mean, you can ask questions in Python also, that's fine. So I know these test labels are 0 to 1. Okay, the train labels are 0 to 1. So I want to map them into certain names, because that's how it is done. The labels have this meaning. Okay, so this is our raw NB convert. So this is not a programming step. This is a programming step. R code, Python code, right? So we map that with a name because it's easy to understand what's going on. We map it, and then I'm just checking what is the shape of the train images. Okay, so train images dot shape will give me how many images are there and what is the each images rows and column pixels are. Everybody's good so far?
Yes.
And then train labels. How many labels are there? 60,000 should be there because there are 60,000 images. Good. And these images are basically like this: t-shirt, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. This is what the 10 different images are. But slightly small differences are there. Taking some pictures and differently and so on. Right. So, for example, I just checking out the first 15 labels in the training data set. Everybody's good? Are you looking at my screen? You are looking at your screen. I understand you are looking at my screen. Huh? So what is this, the train label 5? Which is the train label 5 here? Which is the train label 5? I am printing up to from 0 to 15. Which is the train label 5 here?
2, sir.
2?
2.
No.
0. 0, sir.
Yeah, it is 0. Right? No, not wait. I said 4 or 5?
5, sir.
Oh, 5. This is 0. 1, 2, 3, 4, 5. This is what 2 is correct. First number 2 is correct. Everybody's good? Because it starts with 0.
0 will start.
Ama. Python always starts with 0, right? The index. And I'm saying this also 0 to 15, right? So the first image is actually indexed as 0.
0 is.
So, 50 images 0, but if I have index 5, then it is 2. Maybe I should explain like that. Okay, 50 image is 0, but if I am looking for 50 indexed image, then it is 2. Everybody's good? Likewise, test images are 10,000 of them are there, and of course each image is 28 by 28. Good. Now I just want to know length of the test labels. 10,000 now should be there. And then test labels are, I just do the whole 10,000. Do that, it says it's an array. Everybody's good? There are 1, 2, 3, 0, 1, 2, 3, 4, This is 9,999 number indexed, right? 9,998 indexed. This is 9,997 indexed, right? And what are the class names? We already defined the class names already. Class names are like this, so it should just recall that, and this is what it is. Now I want to see the first image. First image means index is 0. Everybody's good?
Yes.
I'm just basically saying plot, image show train images. This is what the data set is. Train images are for the first train images. I'm looking at it, and it is basically a boot, ankle boot. It's called ankle boot because it goes up to ankle. Are you able to make sense that it is an ankle boot?
Yes, sir. Yes, sir.
What do you think this one is?
T-shirt.
T-shirt. Pullover T-shirt. So it is T-shirt and top. Correct. But very similar, right? Very similar. That's where the computer also is going to get confused. Some small errors are going to happen. Okay. Now I can print the test labels. 0 to 2 means always remember the right side in Python. Right side is this number -1, right? Okay, so you have to remember all those little details. And then class names. So first element is 9. That's what it says, right? The first element, first test label first test label class is number 9, right? And what is its class name? Pullover. So this is in the test case. This is a training case. Remember, this is a training case. Is a t-shirt top. In the test case, it's different. Now, in the test images, first image turns out to be this one. Image show, test images, color bar. We keep some intensity color bar and so on. Test images, second one. This is pullover. Okay, there's a small difference between pullover and the t-shirt top. Okay, I don't know whether you can see this one. What do you think is this one? Looks like some kind of a shoe, right?
Yes.
Okay. All right. So if I want to see, 25 images, first 25 images, here it is. Can you? This is how it turns out to be, right? And it is not different. It is all about train labels, train data. Remember, train data. So ankle boot, t-shirt, we already saw two of them. This is also got t-shirt top. This is for women though, right? This is typically for men and women together. This is dress. This is called dress. This is t-shirt top. This is again, women's. This is pullover. You see the difference between a pullover and a t-shirt? Basically, pullover, coat. This is a coat. Coat has a, The point is, even if you don't know the names, there are some intensities going on here versus here versus here versus here, all those things, right? So that's how we are going to find out. But let's, I'm just explaining the data so far. Now, on the, so we are also giving the names, go with that and so on. This is the Python programming steps here. You can go over that. Now, in order to do the findings, because the numbers range from 0 to 255, we want to make it between 0 and 1. Everybody is good? That's called normalizing. We do the normalization here. That's what is happening. X train is equal to X train divided by 255.0, and X test is this one. Okay. So you can do this kind of stuff in Python. Okay. Two things you can do at the same time. And then this is the network we are building. You see this one very carefully. So what we are saying here is it is a sequentially built. There is a command, all these commands you can learn, but you just learn by using a few examples. It's a sequentially you are building. What is that? You are flattening the image. So this is slightly different approach. I know it's a kind of convolutional, but much simpler convolutional. I'll tell you why. Look at this one. You are just flattening. What it means is you got every picture is 28 by 28 pixels. Everybody got it? 28 by 28 pixels. Now I want to flatten that picture into 1 below, 1 below, 1 below pixel. So how many pixel vectors I'll get? 1 below, 1 below, 1 below. Instead of 28 by 28, how much I will have this one? Can somebody tell me? 28 by 28, isn't it? Am I making sense? That's what flattening means. That means I take first column, I take it, next column I take and put it below the first column. Third column I take it, put it below again further below. Fourth column I take it, fourth column of 28 pixels, I take it and put it below. So that is what flattening means. So I will get only one column. Everybody understands?
Yes, sir.
Flatten the picture image, matrix of numbers into one big vector of 728. Is it 728 or what is that? 28 by 28 is how much? 28 by 28 refers to 784. Sorry. 784 column of one single vector of numbers. Everybody understands?
Yes.
And again, that the intensity place is preserved here also. Everybody understands? Only cats are going to have certain places in the one single vector representation versus one, matrix representation. Agree with me?
Yes.
Okay. But this is a different type of looking at the image. I'm not talking about scanning the features and so on. It's very different. Do you understand what I'm talking? It's another approach. People have said, oh, this also works. And it works, you'll see. I'm not going through. It's a different type of CNN, but it's, I don't have to do the scanning business, all those things, convolutions and so on. It's a different way of looking at the network. Everybody buys it? We can do the convolutional neural network approach also. Later on we can do that, but let's just do this one first. Huh? So I flattened it, and then I'm taking, I map this into 512 reduced set of neurons. How many input neurons are there initially? 784. And then I reduce it to 512 set of neurons in the hidden layer. Understand? Everybody? But somehow I think, first every 2 or 3, I think, 512 means every 2 approximately, every 3 maybe, right? I'm condensing it into 1. neuron, isn't it? That's what this means. And then I take the values ReLU, that is rectified linear units. That means rectified linear units, now if it passes some threshold, and then it becomes whatever that number is until the passing of the threshold. So that means, if I have only, let's say 100, any number 100 below 100, that neuron gets below 100, I'll make it 0. And above 100, whatever the number it gets, that is what is called the ReLU. Everybody understands? So ReLU is a kind of a bounded function. It takes zeros for some limited numbers, and then it takes whatever that number is. That means the signal is there if it is above some threshold. The signal is there if it is above some threshold, and whatever the threshold, whatever the value is the signal. Everybody understand? But below the threshold, everything is made as 0. We say no signal. Understands? Huh? So that is what is called a ReLU. It's a different type of activation function. For the first time you see that, right? Everybody is good? Do you want to know again what is meant by ReLU? Or you understand? Okay. Get it up. So, and then whenever I take the sample, for every time I take a sample, I will drop 20% of the samples. See, these are all neural network people have to do because they have no process to understand the statistical variation. They are doing it as if it is just a mathematical computation. Do you understand what I'm saying? So all this adjustment they have to do, especially the dropout rate. Am I making sense to you? You will drop out 20% of the observation. You won't use it. You take a random sample, you drop out 10% of the observations. Okay. So, and then finally you create a dense layer where 10 of them are the final output. So you're connecting the 512 neurons with the 10 output classes. 512 neuron with the 10 output classes. Are you with me? That's what this means. And again, you use here the activation function is what is called a softmax. Softmax refers to multinomial expression. Please write it down. Softmax refers to basically multinomial, multiple class representation. Okay, because it is a 10 class, right? There are 10 images, 10 different types of images are there. Everybody understands? Agrees with me? Gauri Shankar sir? Okay. Everybody's good? Gautam, so far, so good. This is called the network architecture. We have created an architecture for the computer to analyze the images and build a network for neural network for us. Everybody's good? So that once the neural network is done, we can predict. Everybody's good so far? All right. Now, you want to compile the model. This is the model. You want to compile the model, but in the compile process, you have to say what is the optimizer method, what is the loss function, what is the metrics you want. So optimizer is stochastic gradient method is one of them. ADAM is another one. Adaptive method. Okay, adaptive method is another one. It uses the second derivative. Okay, you can take it that way. Stochastic gradient doesn't use second derivative. Okay, that's only. So it has some advantages. So people use ADAM quite often. And then what is called the loss is, cross entropy, right? Cross entropy is same as what I call it as entropy. They call it as cross entropy. Everybody's good? Now, what is entropy, right? When we did the random forest, we did it. We learned entropy. We also know entropy for K class, multiple class. And that's what this one is, okay? And then metrics is accuracy. We want to know accuracy to be evaluated. What is accuracy? Accuracy is number of times it is accurate divided by total number of samples. Done. Okay. So once you compile that, you fit the model, train images, train labels, epoch 5. Remember epoch 5? Okay. You take all the 60,000 samples and then drop 20% of them. See, look at this one. Drop 20% of them and build the model. Take another 60,000 samples, drop 20% of them, build the model. That's what is happening. So when I run it, you will see train on 60,000 samples, epoch 1. I am asking for 5 epochs. I can do 10 epochs. Let's do 10 right now. Huh? It will just take time, that's all. So let me do up to this. up to this. Let me do up to this first. Cell, run all selected, all above. Run all above. It hasn't, it hasn't done this one. It has done up to this. Everybody's good? Because nothing is blue in color. It should be, here is blue. Blue is okay. Green means running. Everybody's good? So it has run up to this. How do I know? Just because, it started from 28, 29. This was a previous run, 63. You see this one? It was a previous run. So let me go up and see what is the first step. Okay, 5 is the first number, right? It started. So let me run quickly again one more time if you want. I think the answer is there after that. So let me go over. These are all rerun. Nothing is changed, right? Now I have epoch 10, so I should be able to run epoch 10. Okay, 10 times. Control enter is that one. It's running. Oh, model is not defined. Okay, so I have to rerun this. Oh, it's above. I didn't run this. That's the reason. Let me see. Okay, now it should run it. Okay, it's running. 1 of 10. Do you see this one? It takes 60,000 samples in this case, and it is already with just one epoch, one full run. It is running 80, accuracy is 80%. Isn't it beautiful? I think it's amazing. Second epoch is running 82% first epoch. Second epoch is getting 85%. Already, it's still doing. Third epoch, 88%, 87% already, right? And these are called magic commands in Python. %oops, that will give you all the list of data sets and variables that are there. Okay, I use this command also. %oops, WHOS. Epoch 4 is running. Accuracy is 87 now. Right now. Let's see. Anubhav, சரியா கேக்கலையே.
Number of epoch ஜாஸ்தி பண்ணோம்னா accuracy ஜாஸ்தி ஆகும்.
That is correct. That is correct. Yes. More you run, you get more stable and more accurate. More stable and more accurate. But there is a problem in neural network. It's a overfitting issue. Is there? That's why we are dropping 20%. So drop is used to get more stable results. You can use that drop 20% always. Okay, setup in the setup. Fifth epoch is running. So in the previous run, I had only 5 epochs. I got 8.8821 in the test data set. I'm sorry, in the training data set. And so I can use the test data set also, how much it will predict, and I will come to that. Actually, test data set is 0.8821. Okay, here you can see that in the previous run. Let's see what we get. So I already surpassed 0.8835. There will always be small change, right? Because it's all randomly dropping some observations. It is going to happen that way. But remember, this is a much simplified network. I just took I flattened it. I took, I reduced it, 784 into a 512 neuron network.
How did you arrive at the number 512 from 788?
You can see, you want to reduce that size. That's all we know. We can reduce slowly, we can reduce it, 512. Usually people keep a number in terms of 2 power something. 2 power something. because it's a it's an attitude. It doesn't have to be 2 or something, but it's just you can put any number 400, and then 400 becomes 200, and then you use it fully connected later on, right? You can do those things. You should explore this, as part of your lab work. Supriya, correct lab. And you will explore the same ideas or modified ideas in numbers. In the case of images of numbers, okay? So 9th epoch is happening. So it is always improving because it has learned some information. Remember that it has learned some information it is using in the next iteration, in the next epoch. Almost 90% we got the results. Okay, 90% it is able to accurately identify. It's pretty good, right? 9 out of 10. 9 out of 10. Okay, so it's almost done. And remember, this command is useful because you want to know when you are doing some Python notebook work, you want to know what are the variables that are already defined in your work. And also that command boost is a very good command. I like to use it. Okay, these are all just training information. Remember that, 90% accuracy training. Okay, it also not only did the 90% accuracy for the training, but it also verified it with the testing. You see, that's the beauty of this particular collection of commands. I will verify with the testing. Testing sample is accuracy is 88.3%. Everybody's good?
Yes.
It's pretty good, isn't it? It's pretty good. And the validation is basically you have dropped 20% of the observation every time. That helps a lot. That helps a lot. Otherwise, you are going to do more and more damage to overfitting, more in the form of overfitting. So if I use 88.3, how many of them I can 88.3? How many of them? How many images actually I'm predicting correctly in terms of number of images? It is 52,980 in the case of training. In the case of testing, I am predicting 8,830 images correctly. That's pretty good, isn't it? A machine identifying this. Okay. Now we want to find out, model evaluate, all those things. We already did it. We have all this information. So let's just predict using the model. It's very simple, right? Predictions, you just say predictions model.predict test images. Everybody's good? This is the command you have to use to predict. You have model is the one you developed. Model.predict object tells you how to do the predictions. Okay, so I already predicted running this name, right? It's done. And what is the first prediction? Let's run this, and this is the first prediction. You see this one? It is giving a 10 valued array. Why is that? Because it is going to predict either this or this or these are 10 images, right? It's possible. Out of that, which one has the maximum? That is the one is supposed to be assigned. It is good. Maximum is which one? Anybody? Which one is maximum here? Somebody want to tell me?
9.96.
This is the predicted class. Okay, that is the probability. That is the predicted class. So it is 9. So I want to. This is the first. This is the first predicted value, right? So I want to find out the np.org max. That is the index of that one. That is 9. You got the same thing, right? What we usually got. And what is the picture? What is it predicting to be? Predicting to be ankle boot. That's what class names 9 is. Gives me ankle boot. What's that? That's a name. Ankle boot. So let's go and check the picture actually. Test image 0. Looks like ankle boot, right? Good. Now what is the next prediction? This is how you do every prediction. What is this one? The maximum is attained at this one, right? Which is that one? 0. This one is maximum. Isn't it? which is argmax is 2, right? Argmax is 2, 0, 1, 2. Python, starts with 0. Class name is, I just want to find out the class name, it's a pullover. Let's see the picture. Oh, it looks like pullover, right? Pretty good. So I just to play around, check all these things. I'm feeling happy. Wow, that's good. We can do this thing, right? And then I want to do a little bit more, get a little bit more fancy. I don't want to calculate all those things again. I just find out, first I is equal to 0, and then I run these things, and I get this picture. It tells me at the bottom, what is the predicted, what is the predicted probability, name, and the predicted probability in visual form, bar graph. Like that, you can see these things here. It's 100% predicted to be pullover, good. This predicts the highest probability is 92%. Nonetheless, it is assigned to be anchored. That's good. So I can do a little bit more, play around, get fancy about these things. I printed all the pictures. If I want, I can do it, but I'm printing here 15 pictures, maybe 25 pictures. Oh, 15 pictures. 15 pictures. Everybody's good? So do you think you can do, if I give you test images, 5,000 images of something, what can we take? I always like to call out this example for you, for my students. For diabetes, Kiranali is good. Everybody knows that. Everybody is Tamil people, so you know Kiranali, right? But do you know how to find out Kiranali? Kiranali? Nelly or Nalli? Kiranali, Nelly. Everybody knows. I don't know how to find out Kiranali. My children don't know. Do you guys know? No. Yes or no?
No, we know it is clearly, but don't know to identify that.
That's what I'm saying. It is like, I know the answer, but I don't know how to get the answer. Right? But you can create an app and sell it. Seriously, I'm telling you. People will buy it. Like that, 10 herbals. See, in Tamil Nadu, there are a lot of herbs out there. Beautiful. They are really cool. I think they are very cool. Westerners are yet to copy these things and make drugs, chemical drugs out of it. Before that, they do. You guys should make money. All Indians should make money. You have the knowledge. Here is an app. I don't know who is going to do this. Nobody did it for me. You need a lot of sample. I agree. But you don't need hundreds, you don't need thousands and thousands. You can tweak it in such a way that you can make it work even with hundreds of samples. Do you agree with me? Yes? So here is an assignment, money-making assignment. You can get whatever you invest in this course in one app. Imagine this will be a great app for all of India. Just 10 rupees. For Indians and Americans, $1. Maybe. I can sell that, I think. But I don't think Kiranali grows here. That's a problem. Okay? Do you think it's a good idea? I think it's a good idea. Who wants to work with me? Gaurijan, he is bored. Guys, guys should be bored. Why are you hesitating, thinking? Look at that. I have people sitting there. Let me see. Okay, I'm going to work with you, Mr. Gaurish. I'm seriously telling you. But very easy to do this project. What? Go take Kiranali pictures in iPhone. Or what is that called? You have Android? Go take it. In different shapes. Different angles. High resolution pictures. Are you with me? And what else you should take? Non-Kiranali. Do you understand what I'm saying? Because we have to know whether it is Kiranali or not. You have to compare it to something else. That this is not Kiranali, this is Kiranali. You have to know that, right? We can do this exactly same thing. And how will you apply it? You bring your, you go around in the garden. In India, I'm saying, right? In USA, something else. Go around, I don't know, Amma, what is this? Go and find out. Okay, this kid goes, takes this iPhone. Click, click. It will say, like this below, it will say, Kiranali 70%. Or Kiranali 90% is going to say. Oh, I got it. You see this? what I'm saying? You guys should be, okay, that's one example. What is the example? Can somebody think, oh, this is my famous example. I want to do this. Can you guess anything else? Forget about privacy issues. We don't want to get into privacy issues because you can do also other kinds of things also. I don't want to think in those lines. Somebody? And you can do not just Kiranaji alone, Gauri Shankar. You know, there are three things. Great, we call it as Surna, right? Surna means powder, right?
Surname is powder, yes.
Surna is powder. There are three powders which are very, very important, okay, for health. One is Inji powder, Inji. Powder, which is Inji powder, you don't say that, Chukku powder, right? Chukku powder, right?
Chukku powder.
Chukku powder, right? That is very, very important. That's, you are supposed to eat during lunchtime, after lunch, okay? Before lunch or after lunch? I think before lunch. Yeah, before lunch. And the other one is Kadka powder. Have you heard of that?
For coughing.
It's good. It's good for a lot of things. It's supposed to be wonder drug. Okay. So if somebody tells you here is the powder, take it Kadka powder or Chukku powder, you don't know whether it is true or not, right? Now you can do what we are talking. Yes or no?
Yes.
But I don't know whether it is going to be an app you can sell. Oh, Sukumar came a little late. We have been having fun time. Mr. Venukumar, we have been having fun. Okay. Think about all these things. So I'm asking you to think about, to write an app. Enna Supriya, all idea va?
Sir, but instead of these powders, maybe we can try for banana varieties. These days, people don't know which is what banana, which is kill banana.
Right? Maybe others know a little bit, but kids will love it to know. Appa, I found this, I found that. This is going to be fun. You can do banana variety, you can this, you can do that, this and there are so many things we don't know. We will never know, right? Because of late, our parents don't. I don't think our children know it because we didn't teach them. If you live in a village, you learn it through the process, through our daily life, right? Living in a city boy or a city girl, you won't know. You're living in USA, forget about it, right? So, I am imploring every one of you to think about one image recognition app you should do before you get out of our institute. Or even after you get out of it, you come here, work with us, let's create one. It's very simple. If you commit, I will make it a app available, market it. That's what I'm trying. If you commit, I'll market in USA. Big deal. India, they may not care. Where they'll say, Amma will say, or Appa will say, hey, shut up, why are you doing this? You bring it, I'll tell you what it is. Why are you wasting money? Fatruba. Right? But that's not the issue. The issue is fun. The kids will love it. They'll go around taking pictures all over their garden. And they'll say that, apart 90% of them, we don't know. So let's build an app to make sure that we can identify 90% of them. One thing to do, I encourage you to do, if it is good, it will sell. Believe me, world needs these kinds of things. Okay. All right. So that is what I want to share with you on image recognition. Okay. We talked about convolutional neural network. We also talked about a flattening method, which is different, right? Flattening method and out of. Basically, very simple. Okay. Now, when you come back, I'm going to teach you. Take a 15 minutes break. When you come back, I'm going to teach you reinforcement learning. Okay. All right. Is it good, everybody? Any questions? No questions. Okay, take care. Thank you very much. Come back in 15 minutes.
Recording, sir?
Recording, I'll pause now. Resuming the recording. Thank you. So we have next important topic. Gauri Shankar, Marleno. Okay, Gautam, that everybody's here. Very important topic. As I told you, I want to set up the thinking a little bit here. Let's see. Okay. So, what I want to talk to you is, the following. That is, these are actually the real thing that happens through this particular type of algorithm. See, there are different types of algorithms that we can build for AI purposes, okay? This reinforcement learning means it is reinforcing itself again and again and again on the already accumulated knowledge. Did you get it? By repeating the process. Repetition is fundamental in learning. That's why I love this Indian approach. They don't like that actually, but I don't think what they do here is also 100% correct. They have to modify in India also the learning process, which is not just repetition, but also think about it and repeat. Okay? Think about it and repeat. That's what they say, but it has diluted to a level of just repetition. But nonetheless, repetition, by repeating it, you learn. You continuously modify your, this is correct, this is not correct, this is correct, this is not correct. Imagine when you keep on doing that, how strong the knowledge gets accumulated, the correct knowledge. Agree with me? That's the idea. Very simple in a fundamental way. So you will see examples like, stunt maneuvers in a helicopter, right? Stunt maneuvers means helicopter is supposed to have this rotating blade atop. You can actually have rotating blade at the bottom, and still it will run. It will fly. Does it make sense to you?
Yes.
It's all because of this kind of reinforcement learning. You can create that kind of situation. But I'm not talking about huge big helicopters. At least at the test level, small model helicopters. That defeat world champion at backgammon. Defeat world champion at Go game, manage an investment portfolio, control a power station, make a humanoid robot walk. Many different Atari games better than humans. Computers can play Atari games. Atari games was one of the first games that came in the computer world. Have you heard of it? Have you played it? I used to go crazy when I was a kid. When I was a kid and when I came to USA, I was going crazy because I love to play this, what is it called? It's called Atari. What is that?
We know only Pac-Man, sir.
Pac-Man, PSE, Pac-Man, right? That's what I'm telling you. That's one of the first, most famous Atari games. Actually, the first Atari game. So famous, so crazy. I used to go crazy. I was just, I went to a friend's house. When I came to USA, I visited in the summer. First summer, I visited one of my friend's house. We were just going glued to the TV. It's a silly game. It's just glued to all of us, all these adults, graduate students, sitting and playing and jumping up and down. But the reality, what I'm saying is that the reinforcement algorithm can do a better job than us. Okay. At that, we have that level of reinforcement learning algorithms developed in our process. Okay? So we want to see what it is. Now, there was Alpha Go. That was a program that defeated human champions. Alpha Go program that defeated human champions in the Go game. And the machine built by Google, which actually Google bought that company. That company built this game, AlphaGo, bet the human champion. But what they found out, and the AlphaGo, you have to give the training sample. See, whatever the champion played, other people played, all those games, they loaded it. And it was playing against those things. Okay, now in the second variation, they built another machine called AlphaGo 0. That means it doesn't need any input. It does not need any input. It plays, it fails, it learns, it should not play that. It plays, it fails or it succeeds, but in the beginning it will fail a lot of time. Are you with me?
Yes.
And eventually, that machine, which we did not feed any games, what is good game, what is bad game, we did not feed anything. We just gave the rules. We just gave the rules. And it figured out how to play, and it figured out how to beat AlphaGo, the dad. It's scary, isn't it? A machine learns itself and beats the world champion's champion. Isn't it scary? A machine learns itself and it beats world champion's champion.
Yes.
And that's
This is
what.
what Judgment Day.
Judgment Day.
Judgment Day, yes, it's like Judgment Day. Well, but remember, as I said in the beginning, in order to make sure that we don't get really scared, I told you one thing that right now that development is only within the box solution. If you just take that, put it outside the box, the machine won't know how to react. That's a good news. In a way, it's a good news, right? So, and there are layers of human intelligence. I don't think, because the humans will always change the rules of the game. That's a problem with humans. The moment the rules of the game is changed, the AI is gone. It doesn't know what the rule is, what heck this rule is, how is it going. Before it figures out, the humans will change another rule. So there is some hope for humans. Okay, welcome, Gauri Shankar. There is some hope for humans, no problem. I feel that way. Okay. Now, how what does that mean? How do we build? How do we create that kind of solution? That is what I'm going to teach you. Okay. I also want to tell you that just read these quotes. AlphaGo defeated Lee Sedol, the world champion of the Go game, a Chinese board game that has more variations than chess. It was trained by humans, AlphaGo, not AlphaGo 0. It was trained by humans as to how humans play and win the game using data as supervised learning method. AlphaGo 0 trained itself from step 0, absolutely ignorant of anything, learned purely from reinforcement learning without human data, guidance, or human domain knowledge beyond game rules. AlphaGo 0 defeated AlphaGo and it did it 100% of the time. According to the development team manager, the new insight is the algorithm is more important than data and compute power. Okay, the algorithm is more important. They'll say after a while they'll say data is more important than algorithm. So don't worry, but that's fine. Sometimes you want to hear from winners what it means for them to win, right? So a winner always has something to say, and we all want to listen to that. Okay, so the foundations of reinforcement learning are based on what are called Markov decision process, okay, and dynamic programming solution. Two principles: Markov decision process and dynamic programming solution. What is a Markov decision process? What it says is that given a state, a place where a decision is made, a state where a decision is made, the decision maker, we will call them as the agent, okay, decision maker, has to make the next move. The best move for the next move completely depends only on the current state of information and the next state. That's it, only two states. That is called Markov process, Markov decision process. Okay? You understand what I'm saying, everybody? Now, what dynamic programming solution says is that given an end point is maybe success or failure, outcome. That given the end point defined as success, among all paths that exist from the current state to the place only matters, not the past. Okay, those are the two logical principles that will help us solve the problem. There is a theorem for dynamic programming solution. There are calculations to do in dynamic programming solutions. There are decisions to make using MDP. How? Different possible pathways are there to reach the end. Some of them are failures, some of them are success, right? Different pathways. And those pathways, you take the present value at the next step. Because you remember, Markov decision process is current state and the next state only. Between these two states only decisions are made. What we are saying dynamic solution is that all the future pathways from the next state, you take a present value of that and find the comparisons of the maximum present value, positive value, good value, reward, good reward. You take that path. Are you with me? Very simple, right? Looks very logical and simple. Only two parts. First part is a decision from next, from this state to next state depends on what is called depends on the Markov decision process. That is called Markov decision process. Okay, there is some mathematics we have to do. Math is the king or queen here. But the next state, is supposed to capture all the value, all the values of each of the pathways that will lead to the success. Among that, the one which has the maximum value in terms of maximum reward, you pick that one to make the decision from current state to the next state. Are you with me?
Yes.
Excellent. You have understood how decisions are made. So you are learning dynamic programming. What is the principle called Bellman equation? Okay, that helps us to get this, present value for each of the pathways that leads to the success from the next state. And then the Markov decision mathematics from current state to the next state. You combine these two, you solve the problem. And then in the end, we will go through a program. Okay? Everybody's good? So far, you heard some terms, Bellman equation, Markov decision, just retain them. Markov decision process, Bellman equation, dynamic programming, present value, and there is some discounting process also is needed because value goes down in future as we move to the next step. So there are many phases to reinforcement learning. It has engineering, it has computer science, it has neuroscience, it has psychology, it has economics, it has mathematics. Okay, so computer science and engineering combined is called optimal control. And machine learning, engineering and neuroscience is called, reward system, machine learning, all those things, right? Engineering, computer science is machine learning and optimal control. Mathematics and the economics is operation research, bounded rationality, and classical conditioning. Okay, things like that. The point is reinforcement involves all these concepts. Machine learning, reward system, classical conditioning, bounded rationality, operational research, and optimal control. So alpha goes zero, actually, look at this one. There are so many problems that nowadays it is solved, okay? So it's not one or two. Look at this one. StarCraft game, Dota game, poker, video prediction, cycle, GAN problems, generation network, generative network, image captioning, image classification. Okay, all these things in the middle of all those things is what is solved by AlphaGo 0. So what is the benefit of Markov process? You don't need the memory of the past at a particular point in time. That's what the main point is. And you don't need the full memory of the future. You need to know only the next step. And next step has multiple possible operational pathways and their present values. Yes?
Yes.
Okay. Life is very simple. Looks like that, right? Once you think that way. Okay. So generative adversarial network, I said I don't want to talk about it. You can create, painters, for example. You mix the fake and real. Then you create a new type of, new type of painting, music, all kinds of things. These are called generative adversarial networks. All these things are possible. Okay. Very important characters that reinforcement learning learns by playing more and more and more and more situations. You can call it as games, fine, because games situations are fully fixed in there. So in the case of, they figured out, the machine figured out in the case of Atari game, for example, by playing more and more on games, after 600 training episodes, that tunneling will speed up their winning. Tunneling will speed up. That means you create a block. There are different Atari games out there. One of the games is you have to hit and remove all the blocks and then go and then hit back. All of them will fall off. You know what I'm saying? You go hit, remove all the blocks. When you remove all the blocks, don't go and hit every block. You don't need that. Once you create a tunnel, you just keep going through the tunnel, and then if you hit it from behind, everything will fall up in one shot. Am I making sense? All these things it learned itself. Human kid may not learn it quickly, but after 600 games, this reinforcement learning did it. Are you with me so far? Good. Good. All right. There is no supervisor. I told you. Feedback is delayed, not instantaneous. Time really matters. Sequential, sequentially happening. Agent's action affects subsequent data it receives. All right, these are all just an idea here. I talked about this. So at every, so there is a time period. Let's say 1 to T, capital T, time period steps. Each step involves a time period. Okay. A reward at time T, small t, is RT. Okay, reward. So we need the rewards, we need probabilities, we need discount rates, probability of success, right? We need probability of success, we need rewards at every point, we need discount rates, we need the agent, we need the actions. Okay, so there is the action, status at particular point in time, action at particular point in time, based on the rewards at a particular point in time, next time. So T plus 1, there are only two things you are comparing, right? T plus 1, T plus 1. At T you have status, what is the current status, what is the action you are going to take, possible actions. And then what is the reward at T plus 1? Of course, reward at T was already used to reach T position, reward at T plus 1. And multiple rewards are there based on the multiple pathways that can lead you to just success. The one which maximizes the reward, you are going to take it. So far so good. All goals can be described by the maximization of expected cumulative reward. Do you agree with this? Because this is so fundamental. The expected cumulative reward. That's what matters. If you want to become, let's say, a great data scientist, there is a sequence of steps you have to take. And each step you take will have a probability of success. Correct? Everybody? And then it's reward. Sometimes you want to take a slower step, right? In the sense, because it may give less number of rewards initially, but you train, you want to train in the beginning, you want to spend your time more and more to enrich your knowledge, enrich your thinking, enrich your ability to solve problems, enrich your speed of developing solutions, so that when you go into the industry, boom, you may get 2-3 times your salary very easily. Are you with me? So so there are different strategies people might follow, but in general, I'm saying, for a machine to do that, we make it simple. It has to make a decision, yes or no, whether it will take this decision or this decision or this decision. It should be very simple, right? In that case, you take the expected cumulative reward of each pathways. There are different pathways to reach success, but expected cumulative reward of each pathway at the next step, bring it down to present value of the next step and maximize that one, and that is your decision. You are with me, everybody?
Yes.
Excellent. That's all we want to know. And I don't want to spend too much time on the mathematics of it. Bellman equation, I can prove it to you. Maybe in my recording, I will prove it to you for you. Okay? But What I want to tell you is that no, reinforcement learning is a kind of monkey, basically. Okay? But the one thing about the monkey is that it knows what is meant by reward. I mean, we do this all the time. Reward kudukrana. Why? He wants it to act in a particular way, but the reward system can also have built-in communication. I'm not talking about that. You just make the reward to perform only. That is the dog. Dog is not generally not a communication is established only by a reward system, right? So you can train a dog with the right reward system and punishment also sometimes, right? Punishment too. So it's only a when I was growing, they used to tell me that no, just if you give a monkey a typewriter, it will create a Shakespeare. It doesn't have to know anything. Do you agree with me or not? That's what it means to say as n goes to infinity. As n goes to infinity means n is the number of letter typed. Infinity means that's no countable. It just goes years and centuries. It keeps typing. One day it will come out. But what we are saying is that no. This is an intelligent monkey. Oral reinforcement learning is oral. Is the intelligent monkey. It doesn't require millions of years. You give the right reward system, it will do it probably in a year. But that's what this software is. It's an intelligent monkey. I mean, I'm sorry to say monkey because we all think that monkey is bad, right? No, it's a useless, it's lower level intelligence. No. What we are saying is a process to learn, that's what. Okay? So, in my opinion, it is better than, oral is better than randomness. And even randomness can create a Shakespeare work. I know 30 years back, I used to hear these things in probability. Okay? But we are not talking about just random probability. It's an intelligent, rewarding process. If you build that, a monkey will create a Shakespeare work in a very unexpected short time. Do you buy that? That's what we are talking about. How different we are from monkey? Nothing. Not too far. We are creating solutions, so what's the big deal, man? You give right reward, anybody will succeed. That's another thing, never underestimate anybody. You give, if somebody is failing, this is philosophy, right? But I want to say that it's very important philosophy. You give a right incentive to people. It doesn't matter what language you belong to, what religion, what caste, community, gender, doesn't matter. So if there is a failure in society, it's because we don't have a right reward system. I can say that because I live here, I understand. But that's it. That I believe in that. Okay. A little bit of philosophy is over. Let's move on to the right thing, what we want. So in real world, how action happens with the agents? They observe, the agents observe. Observe, agent means somebody who is going to act, right? That's what agent means. Observes, okay, looks at the rewards, and then takes action. That's what happens. Do you agree with me? At least to solve some problems, at least for that purpose, you can agree. Philosophically, you may not, that's a different thing. Okay. So, so that's what is happening here. Let's, I told you, right, all your past act decision making is fully embedded in the previous step. I mean, I said from current step to next step. I can also say the same thing, from previous step to current step, right? So all your past decision making is fully embedded in the previous step. And hence, you can throw away the rest of the history. Agree?
Yes.
That's the meaning of fully embedded in the previous step, okay? And then that is what is called the, and then use that to make the next time decision, next time period decision. Bellman equation says all future decisions are fully embedded in only in the next step, and hence you don't need, you do not get confused by all kinds of different pathways from there on. Agreed? So only 2 period decisions you are going to make. That's beautiful. So there are, in summary, there are 5 things. Environment, that is the box where the machine is acting. Agent, that is the machine. States are different possibilities. Actions are different possibilities. Actions are, you can call it as columns. States are rows. Are you with me?
Yes.
State means different possible states the other agent can be in, okay? And then the actions taken and rewards. These are the only things that determines the reinforcement learning problem. So I'm going to talk to you today an example of a game where the game is, you have to cross only 4 steps, okay? Forward, or so starting point is this corner, okay? So forward you can go, this way you can go, row wise you can go, column wise you can go at every point. But starting point doesn't have left and doesn't have up, okay? And G is the goal. H refers to hole in an IC patch. In an IC patch, H refers to hole. If you fall, game is over.
Okay.
F refers to frozen area. So you start here at S, starting point. So you go to frozen area. You have to reach the goal. That's the end. Then you win. That means you survive. Okay. Now, from if you go down, it's frozen. You are good. You go down, frozen. You are good. You go down. You fall in the hole. Gone. Okay. You took one pathway, and you failed. Napa?
இல்ல இதுதானே சொல்லுங்க.
What is the question? What is the question?
Trying to see the direct approach.
Oh, no. Now you can, of course, you can go here, down, 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 and then go, right? There are many ways you can succeed. Down, 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 go here, go here, go here, go here. Or go here, go here, go here, go here, right? Or you can go here, here, come down, come down, come down, come here. There are so many ways to fail, there are so many ways to succeed, right? That's what you're saying. These are called different pathways from here to here. Some succeed, some fail. My point is, you take the expected rewards for each of these pathways and put it in this set and compare all those different pathways and then make a decision. Oh, this particular pathway is failure, and this particular pathway is failure, and this particular pathway is a success, right? It has that extra information, but here is a problem, right? We don't know yet fully we don't know. So the only way to do is the game starts. It goes down this way, boom, failed. It knows this has to be given less important, this has to be, this has to be given less important. That's the main point. Don't worry about this thing, this has to be given less important. Okay? On the other hand, this, but you don't go this way, but then you reach here, succeed. So there are different values coming in here. One pathway says it's good, one pathway says, starting here, one pathway says it's good, one pathway says it's bad, right? So the game is played so many times, so every time it is creating an incremental value here, and it knows, the system knows that, okay, I need to go here, next step, by playing hundreds and thousands of times. Do you agree with me? Possible?
Yes.
Thank you. If you understood that, it becomes very simple. So there are 16 stages out there. Okay. For S is start, F is frozen, G is goal to reach, destination, the crossing of the river or crossing of the ice patch. Simple 16 stages are there. Okay, I'll come to that. And here is the computer learning process, reinforcement learning for that. Okay, let's build that one. Okay, one moment, please. Okay, everybody seeing my screen?
Yes, sir.
Okay, so you have to use NumPy because all matrix calculation, all array calculations are done using NumPy. There is a package called Gym, okay? And and there's a package called random time. All these things I want to download. Display is also what is needed for me. Okay. So in the bottom, I have a solution graphically done here. Take a look at this one. Start and go, right? Everybody see this? I replicated here. So you will see that now how it's moving in different ways and then how it is going to win. Okay, everybody's good?
Yes.
But we have to set up the process. It's a within a box solution, right? We have to set up the process. So there are some things you have to think about, right? So what is happening is that now there is something called explore versus exploit. Those two words should mean something to you. What does explore mean? போய் பார்க்கலாம் கரெக்டா
Yes.
அதான் explore. போய் பார்த்தா என்ன நடக்குது பார்க்கலாம் explore. You all understand Tamil, right?
Yes. Yes.
Sir, Avnish is there with us today, so
Avinish? Okay, let me see, test it out. That's what explore means. Yes. On the other hand, exploit means I already learned something, I want to utilize that knowledge. So in essence, explore and exploit mean the following. I want to give you the definition, very careful definition here. Making a decision as to exploration where we gather more information that might lead us to better decisions in the future or exploitation. Are you with me? That is, it is a process of gathering more information, because when you explore, you don't know, and you want by exploring it, you gain more information. Okay, or where we want the best decision given current information. Okay, first, okay, so where we want to make the best decision given the current information is what is called exploitation, because we already have some information, just use that. But both has a problem. Do you agree with me? Because you cannot explore too much. You have to use your past gained information knowledge. You cannot just sit there with the gained information alone, because you don't have new opportunities, new pathways. Agreed? So you have to balance between these two. Everybody is good with me?
Yes, sir.
Okay. So we want to do the following. At every stage, there are in this game I have 16 possible places in the grid, right? 16 possible places in the grid, everybody? 4 by 4, right? 16 possible places in the grid, they are called states, right? Each of this position is called state. Agree? That's the definition I'm giving you, huh? And the action is 4 possible actions. At every state, you can take 4 possible maximum. Left or right, up or down. The first one doesn't have 4 options. All the left ones will not have, all the left first column does not have all the 4. They will have only the middle point will have 4 maximum. And the top row doesn't have all the 4 possibilities. But the point is, overall, we have 16 states and then 4 possibilities as a matrix. Are you with me? That is your starting point. So we are going to create this Q table, which is a value table. Q table is also value table. Okay. We create, if I am in state 1, should I go up or down or left or right? That's what I have to make a decision. That's what each of these row means. Okay, everybody?
Yes, sir.
Okay. Now I have created this Q table, which is the value table, right? To make a decision which pathway I have to take, with which step I have to take, left or right or up or down, right? And it is 16 by 4. Look at this one. Q table shape is 16 by 4. Okay. Everybody? Number of episodes. I want to run 10,000 episodes to learn and create this RL solution. Maximum steps per episode is, every episode I'm giving 100 chances, 100 steps I will give for it to learn. It's a lot. You don't need that much. I just need to give only the 100, because sometimes you want to come back, right? All those things. Now learning rate is, I want to learn only 10% of what information I have. Okay. On the basis of that, learning rate, I know the future, I'm talking about the exploration, I will go at the rate of 10%. I don't want to give too much importance, right? Discount rate is 99%, I will discount. I want to be safe, right? And soon. Exploration rate is 1 step, right? Maximum acceleration is 1 step. Minimum acceleration is 0.01 and exploration decay is 0.001. So at every stage, every time I make a step, I decay my learning. I what is it called? Create a decay, that is, reduce its effectiveness in learning on that particular step. Are you with me?
Yes.
Okay. So with all these things, I can create an environment where I will allow the machine to learn itself and then reach this endpoint goal. Okay. So first, what is that? Rewards all episodes is empty set. I'm creating a rewards all episodes empty set. For every episode, in the number of episodes, how many number of episodes I have, I'm going to define. This right now is a routine right now, and then I will call it down below. I will call it how many episodes. Look here, I'm only calling 1 episode in the range. Are you looking at me? Look at my screen. Only. I can make it 5 episodes. Are you with me?
Yes.
Okay, but I can make 100 episodes and so on. But just right now, I'm going to simulate and show it to you how these things work. Okay. It should not be running. Why it's running, I don't know. Okay, it should not be running. Kernel stop. Interrupt. Let it go. Okay. Now, so far so good. Any questions? All right. I want to clear up the environment. Every time when I run a new episode, I want to clear all the previous values. Good? Make sense? And then done false. Done, there is a variable called done. I'm keeping it done as false right now because it says if it is true, it will stop. Okay, it breaks. Look at this one. So it starts, because it's, I just want to clear all the, environment variables and the values, environment variable values. And then, I'm starting it. Rewards, the current state is, there is no reward, just 0 starting point, right? And then for maximum number of steps per episode, that is 10,000. For every step in the 10,000, I will run this. What is that I'm going to run? I'm going to take randomly some value in the range 0 to 1 as a starting point. Okay? And if the exploration threshold is greater than exploration rate, this is threshold, right? This is always less than 1. Do you agree? That's what it means. But exploration rate is 1 if you look at it. If you look at this one, right? So in the beginning it will be less than 1, so it will take the argmax, that is where the maximum value is attained. From the state only, wherever the current state is. State can be 1 or it could be 10, 3, 4, anything, right? As the problem progresses, it will be determined by their previous values. Everybody with me? And if it is exploration rate is, threshold is greater than exploration rate, okay, because the exploration rate will go down as we go along because we are going to take a discounting all those things, right? Look here, exploration rate is redefined. Minimum exploration rate plus the range times np dot exponential of decay rate times episode. Okay, so it will change. Eventually it will change. No worries. No worries. It will change. So and then it will start working. Accumulating the Q table. Q table is what? Q table is the previous Q table. Okay, sorry. The previous Q table times 1 minus learning rate plus 1 minus learning rate plus learning rate, reward plus discount rate. All those things are adjusted here. This is the mathematics I was talking about. I will give it to you as a homework and justify that this is correct. I can also tell you later on why it should work. It is correct. Everybody is good on that?
Yes.
I'm basically saying every time I'm modifying the Q table, the value table. For every attempt of the sample I am going through, for every sample I'm going through, I'm modifying the Q table. because I'm going to take the Q table value to be based on 10,000 maximum iterations per episode. I'm sorry, per episode, 100 repetitions, and such 100 repetitions are repeated 10,000 times. Are you with me? That's what this, that's what this means here. 100. Maximum steps per episode is 100, and how many episodes? 10,000 episodes. Are you with me, folks?
Yes.
Is it confusing? A lot of details here. The only way is repeat nothing else. Anybody can learn. Okay. You are with me, everybody with me?
Yes, sir.
Okay. All right. So this is how the Q table is, and the value table is updated, and then state becomes new state, and then rewards becomes, you add the, current reward, and then if done, the moment it becomes done is, is created here. New state, reward, done, information is, environment dot step action. This is, this is, it is split into these possible values coming out of this environment dot env dot step function. And then exploration rate decay. So I told you that minimum exploration becomes adjusted. It's not one always, right? It was 1, right, in the beginning. So it is becoming adjusted here. I mentioned that exploration is equal to minimum exploration rate plus this. Rewards all episodes. I keep adding the rewards to make a decision. What kind of decision I make? For every 1,000, this is what NP split means. I split the data, 10,000 observations are there, right? 10,000 observations, I split into 1,000, okay? 1,000, and I calculate rewards per 1,000 episodes. And you can see that average reward per 1,000 episodes increases. What does that mean? Overall, it increases, okay? It will go up and down also a little bit, but overall it increases, and here there is down here. But if by repetition, it works. If I want, I can always make another 10,000 more also, 20,000, 50,000, so on. Doesn't matter, right? Computer does it. Computer is cheap. So this is what happens, the Q table. And from that, every 1,000 steps, this is what, improvement is happening. And now I'm making a decision here. Look here. I'm going to say for episode I use that function. That function, what do I define? For episode in range 5, that means only 5 episodes I'm going to run. That means it will run 5 times, 100 times, 10,000. Agreed? You understand what I'm saying? Because every episode is 100 times, and each times it is allowed 10,000 times to play. Everybody's understood so far? Yes, no, Arun, no. Now, what I would suggest is you have to go through this example. Okay, we are going to review this also in the lab. Supriya?
Yeah.
We will review this in the lab. We may have to do 10 times, if not 3 times, maybe 15 times. But Punyo. Okay, no worries. Gautam,
Yes, sir.
Rajesh, Gauri Shankar, everybody's good. We know Venu Kumar, correct? ரொம்ப confusing இருக்கா? நிறைய details. But remember, people did PhD thesis and then wrote, these developments. And you are learning in one day, you want to learn. It takes time. So we will commit that we will be patient, but committed to learn. That's all we need.
சார் இவங்களுக்கெல்லாம் லீனியர் இன்டகிரேஷன் ஃபர்ஸ்ட் லெக்சர்லயே புரிஞ்சிருக்கான். அதனால இது திருப்பி சொல்லி கொடுக்க வேணாமா? இப்பவே புரிஞ்சிருக்கான்.
No, it's okay. It is okay. It takes time because there are a lot of parameters. Why that parameter comes, why that doesn't, why that particular parameter acts in a particular, all these are questions. But your commitment is more important than anything. சாப்பிடாம 4 பேர் உட்கார்ந்து அடிதடி போட்டு எப்படியாவது புரிஞ்சுட்டீங்கன்னா வந்துடும், வரும். You're all very rational people. I told you earlier, right? Everybody is capable. You're all capable. Okay? You have come to the institute, that's a big deal. In my opinion, it's a big deal. You are committed, you have come to the institute, you paid, you have already passed your MS, MA, I don't know, whatever, MBA, ME, BE. So you're all, you have enough raw material. It's up to you now how to train it. Repetition is all about life. Believe me. I cannot say this more than enough. Okay, all right. So what happens is that now I take the Q table for each step in the range, maximum number of steps. This is 100, right? For each step, in 100 steps. For each episode, 100 steps. For each of the steps, you have run 10,000 times. And that is what it is, right? Everybody's good?
Yes, sir.
Okay. So I'm going to run this, I'm going to stop this, and then I'm going to click to go to the next step. See, input, press enter to continue, right? I'm going to run it to you and show it to you, okay? Shall I do it? Everybody's good?
Yes, sir.
And it will create something like this. Current state is 0, the Q table value calculated is this, and then current state after np.argmax is 0, this Q table, I don't know whether I should print the Q table. I should not print the Q table. Okay. And then it says the new state reward done info after action is taken is 0, 0.0 false. Done is false, right? That's what done means. False means done. And the info is this probability, this much probability. Okay, so let's run this. I have run up to this. Okay, I'm going to run this now. Let's see what happens. Okay, something is going on. Gee. I'm going to interrupt this. It's a problem, I feel. It was running all right, but now it's doing marker. Okay, so I'm going to start from the beginning, okay? Run this. First one will take some time because it's connecting to various packages and importing them and making them ready to run. And this was actually written by somebody else. I paid for it actually. So because it's a good example to share. Okay, it's still working. That means it's still there is a problem. I have to disconnect this and call again. Sorry about that. I have to redo this. Shut down this. Run. Shut down. Again, shut down. I want to do shut down. Interrupt. Shut down. Okay. I'm going to close this. Oh, it is still running. That's what I don't have patience, so I stopped it. Okay. So now I want to go back to the home and start here, this one. All right, let's run this. Let's see what happens this time. Okay, guy is ready. Okay, next, I'm accessing the game, Frozen Lake game, version 2, version 1, 0, I don't know. And then I'm setting up the Q table. Okay, everybody's good?
Yes.
What is the shape of it? 16 rows and 4 columns. 16 rows are status, guys. Any one of the 16 state situations, the 4x4 region, right? 4x4 cell region, and then each of the column refers to the action. Okay, action space size. Okay, and then number of episodes is 10,000. Maximum steps per episode is number of episodes is 10,000. I can go up to 10,000, but I'm going to run only 5 or 2. Are you with me? Show it to show you the calculations. And each of the episode runs 100 times. 100 steps it takes. Each of the episode takes 100 steps. Then learning rate is 0.1, discount rate is 0.99. Okay, exploration is 1. Maximum exploration rate is 1. Minimum exploration is 0.01. Exploration decay is 0.001. Okay, let's run that one. Next comes the set up the function. I'm basically setting up the function now, right? Oh no, I'm also creating a run the Q table I'm creating right now. In the end, it is running. In the end, it will print the Q table value. So I'm expecting Q table to be shown here and the rewards for every 1,000 episodes. Okay, these are the rewards. Everybody's good? And this is the Q table at that time. Now I said I'm going to run only 2, and then I have 2 iterations I will show you, and then you can run it for 10 or 100 later on, or 10,000 maximum. Okay. So here you see this one. This is what this means. Input, press any key, right? That I want to stop there so that you can understand what's going on. Ready? Let's run this. Okay, episode 1. Current state is 0. Current state after NP is 2. Okay. Up or down, left or right, right? So now I have to press enter to continue, then it will go to the next decision making. Whatever. Okay, so current state is 1. Everybody?
Yes, sir.
It moved there. This time argmax is 3. Okay, current state is new state, reward, and all those things are here. 0, 0.0 false, and this one. So let's do it. I mean, I'm just for the second iteration, right? Remember that it went back. Now it is learning again. So it keeps on learning. There will be a time, and it will say it reached. Look at this. It's moving to different places, right? It's trying different things. Are you with me, folks?
Yes, sir.
Cool, very cool. So it went back up, left, right, up. It cannot go. So it is just doing right, left, and went back, right, up. It cannot go. So it's going like this. Let me do it a little bit faster. Oh, yo. Sorry about that. It was introducing space here. My mistake. I didn't mean that. Okay. This should be only here. Okay. AI. So if I do it faster, it puts a space there. That is the problem. Okay. So it will learn like this slowly, but let's make it faster. Can I do that? And then
Yes, sir.
you will see. Now I'm going to take this out. I don't need this. That is what is holding me to give the input, but I will still give, how about this? I give half a second to stop at these places, so that, you know, here also I'll say time sleep is half a second. How about that, Let's run this now. Oh, it is still waiting. You remember, I have to see, it is still waiting in the previous stop, so I have to stop it, interrupt the kernel, and then start. Everybody's good?
Yes, sir.
Kernel, restart. I'm not sure whether it will start from here. Let's see. Otherwise, I will rerun it from the beginning. Okay, so it won't run because env is not defined. Okay, that's all right. I'm just telling you, how to read this program, right? Okay, now it is done. Come on. Okay, it's done. Cool, very cool. It's all moving. Q table, maximum episodes, rewards. The function, the Q table is getting created, and then rewards for every every 1,000 steps. It's going to print, and then I'm ready to run this one, and I will run 5 complete run, and it will see, you will see when it succeeds, when it fails, and so on. Okay, quickly it will run very fast. So it's done. Now let's go run this maybe 10 times. Okay, I can go up to 10,000 times. That's a parameter setup, but I'll do 10. Okay, everybody's good. Let's run this here. Okay, episode 1. Remember, each episode can run 100 times, right? And there are 10,000 episodes you can do. So within 100 times, let's see whether it will reach the goal. But it is learning though, right? You'll see. It's not moving much. It's all based on the random values, but then after a while it keeps accumulating, right? So it has better chance of moving around. There you go. It is better behaving now. Oh, very close, very close. Oh, it went back. It was trying to learn more, right? Ah, there you go. After 15, what is that? 15 steps, okay? It reached the goal. It learned. Are you with me, folks?
Yes, sir. Yes, sir.
Good, 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 good. It went back. You see this? Because the discount rate, decay rate, all those things, exploit versus explore, all those things play a role, right? Because it won't explore very fast. It doesn't want to, explore very fast, right? You remember, learning rate is 0.1, decay rate is there, and also the incremental weight is 0.001, all those things. So, oh, it fell. I think not it fell. It did not fall. It did not fall. That's why it's still there. There you go. You see, second episode reached after probably 30. It's learning. Again, this is the third, right? You see, the first episode took a lot more time to come up to this level. Do you agree?
Yes, sir.
But it is coming much faster of late to the state 4 and 8. This is the third, right? Third episode. I have only 5, right? Oh, 10. I put 10. Okay. All right. So that is what I want to share with you about reinforcement learning. Okay. Any questions? I'll give you this. It is recorded, and I will also give you the program. I'm accumulating, maybe another program for you for image recognition, and for this one also. But I have to do. I have another program also. Okay, how to allow a physical, physical weight to balance itself. You know what I'm saying? Physical weight, standing on a platform, right? Like perpendicular. It doesn't fall left or right completely. It will fall initially, but then it will figure out how to balance itself by adjusting the weights and so on. Are you with me? I have that one, which is a very commonly used. It's called cartwheel. Okay, cartwheel example. And then I also want to bring it up to you RNN nodes. Okay, that is recurrent neural network. Everybody good? Everybody good?
Yes, sir. Yes, sir.
So while this is happening, iteration, I don't know what number I should put iteration number here. Okay. What do you think, you have a chance to use this kind of stuff in your office or as an app to write? Remember, this is not going to happen all the time. You are not going to be learning. You are learned and you create the algorithm, put it in your app to apply it, right? It's not that it's going to learn, when somebody buys the app, it doesn't mean that, you are going to learn when you buy the app. The RL, reinforcement learning, is behind the screen in your app. Do you understand what I'm saying? It's like AlphaGo game player. It is behind the screen. It's not learning at that time. It has learned overnight or previous week, millions of times, billions of times playing itself. Am I making sense? So your job is to develop the algorithm so that is usable in practical applications. And what is the practical application you can use? You may think about it. That's also another assignment for you if you don't want to say anything now boldly. NSR Gauri Shankar sir, correct? நீங்க ஹெல்த் கேர்ல தான் ஒர்க் பண்றீங்க இல்லையா?
இல்ல சார், இப்போ வந்து ஒரு ஹெல்த் கேர் கம்பெனில இருக்கேன் சார். ஹெல்த் கேர் இல்ல, ஆக்சுவலி இந்த ஐவிஎஃப் இருக்கு இல்லையா, ஐவிஎஃப்கான லேப் செட்டப், அப்புறம் அதுக்கான intrinsic vitro fertilization test tube.
Okay, so what is the problem there you are solving? What is the complex issue that they have tough time resolving?
No. There isn't any major problems there. Actually, it is my one of my relatives' company, so they have taken up the project there with them. I'm trying to implement this. Implemented our concepts there. Checking, getting the data, sanitizing it, showing them the dashboards, trying for some model building there. How they can increase their sales. That is what is the first thing that I have taken up. So it is not a big company, but somewhat right now I have sanitized the data. I have got a set of data and discussing with the stakeholders like the owner and the sales team, how they are doing the sales, what are all the advertisements they are carrying out. All those details I am collecting with them now.
When you are using image recognition, text analytics, when you are using RL, recurrent neural net, RNN, recurrent neural network, or reinforcement learning, you are in the areas of AI, direct AI. Not every algorithm is AI, but even though people would like to say like that. Okay, it's a hype right nowadays. But think about what you can do with image recognition. You can do a lot of wonders because image is 80% of intelligence. That's how humans process information. So there is so much of an opportunity available. In Arun, correct? Please think. இப்பதான் எபிசோட் 6 வந்துருது. ஏன்னா நான் அது ஸ்லோ டவுன் பண்ணிட்டேன். அது முடிஞ்சிட்டோம். இல்லைன்னா அது இப்போ நான் இன்டர்வியூ பண்ணேன்னா அது எங்கேயா போய் மாட்டிக்கும், வராது திரும்பி. அப்புறம் நான் டிஸ்கனெக்ட் பண்ணணும், இன்டர்ப்ட் பண்ணணும், ஷட் டவுன் பண்ணலாம். ஓகே, the point is I really want you guys to think about what problems you can solve in your office or for your vision. Kiranelli is my vision. My interest. It's just for fun, I'm saying. You can do that with me. I'm fine with that. Gauri Shankar is going to do correcting lab. Yeah. Interest in that's okay. If you have time, ஒண்ணும் கிடையாது. எனக்கு கீழே நீங்க இருந்தா நான் போய் ஒரு 100 பிக்சர் எடுத்து அனுப்பிச்சிடுவோம் உங்களுக்கு. இல்ல எங்க ஊர்ல கிடையாது கீழே நெல்லி. அது எங்க இருக்குன்னு தெரியல. ஒருவேளை பாக்குறேன் நான் I will do research. But the point is, no, I have to be in Florida to grow or California to grow. Not yet. Maybe a house here வளர்க்கலாம்னு நினைக்கிறேன். But not only kidney nalli, there are a lot of medication for diabetes. Venthium is good. Okay. There is also evidence. People say that Chukku is also is a lowers glycemic index in the food. You know what I'm saying? Glycemic index is an indication of diabetes. Okay. What food? So every food is ranked by glycemic index. Okay. The more the index, it is considered to be bad for diabetes. That means it has more sugar to process in your body. So episode 8 is now running. Okay, so I encourage you, if you don't think about any of these usable applications immediately in your job or for your vision, I haven't really encouraged you to do something useful, which I will not consider as success to me. I want you to get excited, use them. இது கஷ்டமா இருக்கும், difficult இருக்கும், புரியாம இருக்கா போல இருக்கும், எப்படியோ நம்ம பண்ணுவோமே. Bring it. Somebody from the institute will help you to grow progress. Okay. So with this, I want to close this topic. As I said, I will give you this program. I will also give you one more program on cartwheel for RL. I will give you one program number identification in image recognition. I will give you that. Supriya will run that with you as a lab. Supriya, correct? பண்ணலாமா? அது பண்ணுவோம். அப்புறம் RNN I will record and post it. By the way, I recorded what is it? என்னப்பா?
SVM part 1.
SVM part 1. உங்களுக்கு அது எப்படி ஃபீல் பண்றீங்க? Is it good? Is it
part 2 நீங்க அனுப்புங்க, அதுக்கு அப்புறம் தான் நான் ஷேர் பண்ணுவேன்.
ஓகே சரி. part 2 ஒண்ணு இல்ல, நான் அந்த எக்ஸாம்பிள் இருக்கு அதை ரன் பண்ணுவோம். அதான் என்னோட ஐடியா. ஓகே. Part 1 I have explained the theory. எப்படி அதுதான் hopefully, because I kind of used the moving art, moving graphics to explain. My idea is that by doing that it is easier on you to understand. So okay, I will send that. I got a lot of work to do, return to you folks. Okay, I will do that. I think it's kind of last one. So that's all I have for ML. Any questions, any topics, any botherations, talk to me. It's your time. Rajesh. இது அடிக்டிவா இருக்கா கம்ப்யூட்டர் ப்ரோக்ராம் போயிட்டு இருக்கிறது? டாக் டு மீ. அது நான் முடிஞ்சிடும். Any botheration, any questions? We have given a lot of case studies also. Do you agree with me? Because there seems to be 9 is going right now, only now. That seems to be a common issue. No, sir, example. I'm going limited time. We actually give more hours to you than colleges. Do you know that? Yes or no?
Yes, sir. Yes, sir.
We give a lot of hours. And we also give you a lot of examples, a lot of time I spend in personally with you folks. So my question is, what bothers you, what worries you, what you want, which we could make it available more for, at least for the next students. Talk to me. If you don't want to talk to me now, please talk to Supriya. Okay? Is that okay?
Sure.
Enjoy learning. Automation is very, very important. I ended up the course with an automation right now. Automation is very, very important. Please learn automation. You can impress people. Even a small regression, if you automate it, people love it. You reach the goal. You understand what I'm saying? Of course, you reach the goal every time. You remember 100 chance I give, right? 100 runs I give for every episode, and there are 10,000 episodes, and from that it learns, it knows how to. So I store this as an algorithm and then recall it in the application. That's what the idea is. So I can create an algorithm to play against you, right? And then you will see that it will win because it has all the things recorded. It knows how to go fast, quickly. Of course, this is a very simple problem. Humans know how to go there, right? It's very easy. But that think about it. If you make it as a complex problem 10,000 times or 1,000 times complex than this, humans will struggle. That's a reality because computers are brutal in speed, and they learned overnight sitting and playing this itself. It doesn't get bored. And can you play yourself chess game? No, impossible, right? but it can play itself chess game and learn to be a champion. That's all I have on my side. Everybody, thank you very much for the opportunity for to teach you. I think I look forward to seeing your success. Is it a good expectation?
Yes, sir. Yes, sir.
3 பேர் தான் சொன்னீங்க. யார் 2 பேர் சொல்லல? தெரியும் உங்களுக்கு யாரு.
Yes, sir.
ஓகே 4 பேர் சொன்னீங்க, ஒருத்தர் சொல்லவே இல்லை. கௌரி சங்கர் கேட்கலையா உங்களுக்கு?
பேச முடியாம உட்காந்துருக்காரு.
ரொம்ப
இங்க வீட்டுல இங்க வெளியில பசங்க கொஞ்சம் கத்திட்டு இருக்காங்க. அது என்னது அப்படின்ட்டு காது கொடுத்து கொஞ்சம் என்னன்னு அப்படி அந்த பக்கம் பாத்துட்டு இருக்கேன்.
Okay, சரி சரி. Okay.
Sorry.
All right. Thank you very much, everybody. That's all I got for you on ML and PA1, PA2, and so on. I hope to see you, with exciting news about you every now and then. Looking forward to it. Bye-bye, everybody.
Bye, sir.
Bye, sir.
Bye.
Bye, sir.
What a reaction.
Bye.
Onella, sir.
Okay.
Onella. Okay. All right, sir. I will talk to you tomorrow.
Bye.
Bye, sir.
Yeah. We will talk.